and I probably gave you a couple of assignments. Uh, did you have any issues with any of those assignments? Please let me know.
No, sir.
Okay. Okay.
Sir, in the FQ, in the second assignment, uh,
Okay.
when the load is given in the linear form, q naught 1 minus I by 2 plus q1 1 plus I by 2, uh,
Yes.
then after the n matrix, we have to multiply every term. That means the xi into every n term, we have to multiply the q naught 1 minus I by 2 and also the q1 1 plus I by 2.
Yes.
In
So the thing is, whenever you are multiplying, um, how should I say? Whenever you are multiplying a vector with a scalar, so that scalar must be multiplied to each and every term or each and every component of that vector, and same applies to a matrix. Okay,
Okay.
and there is another way of doing that. For example, if q shows a variation, if is not a constant, then let's say if you are doing this integration, j times d xi, uh, so you have your n transpose, which I believe in this case is a column vector, which kind of looks like this: xi times xi minus 1, then by 2, 1 minus xi squared, and the last one being xi times xi plus 1 by 2. Okay, I may be wrong, but let's say this is the this is how it looks like. And then you have your q, uh, which is a scalar. Okay, and it is somewhat like this. um okay, so it is 1 plus, sorry, 1 minus xi by
Xi by 2.
1 plus xi by 2 times q0 q1 maybe. Okay, or q1 q2, whatever the case may be. So you can
Okay.
also write it like this: q0 q1. Okay, and this thing you can call some other matrix. Let's say you can call it matrix A, so you can put it over here. Okay, now the size of this matrix is 1 cross 2. Okay, and this one is 2 cross 1. So, and this one is 3 cross 1. Okay, so there is no issue in multiplication. Okay, and actually this product of two vectors, okay, this is known as dyadic product. Sorry, dyadic product. It is exact opposite of the dot product. You see, dot product, if I assume that all the vectors are by default column vectors, okay, like this: a1, a2, a3, assuming it is three-dimensional. Okay, and b is somewhat like b1, b2, b3. Okay, so a transpose b is essentially the sum ai bi. I goes from 1 to 3. Okay, and in that case, the number of components should be same in either of the vectors. So this particular expression is essentially a dot b. Okay, and that gives you a scalar out of a couple of vectors. Okay, so this product of vector that gives you a scalar is called a dot product, or so-called inner product. Okay, that's the generic term. So this dot product comes with a single dot, and this single dot has this meaning that that earlier the participating quantities were vectors. Okay, that means they were something called the first order tensors. How do I know what order a given tensor is? Let's say this is a tensor. Okay, this hollow p, this hollow p is a tensor. Okay, and if I write p I j k l, if I can represent any component of p as p I j k l with 4 indices, then it's a fourth order tensor. Okay, and since for vectors there is only one index that I can use, so these are first order tensors. So when you go from first order tensor to a scalar, you you lose, kind of one order of tensorhood, so called. Okay, I don't know whether it is put in a correct sort of term. So this single dot has that meaning. Now what is a dyadic product? Dyadic product is, let's say if I do a b transpose or b a transpose, so that also is allowed. You see, a has a size of 3 cross 1 and b has a size of 3 cross 1, but when I take a transpose it is 1 cross 3. So the product matrix would be the product would be a matrix, okay, of size 3 by 3, and that would kind of look like this: a1 b1, a1 b2, a1 b3, a2 b1, a2 b2, a2 b3. So uh, with row, when row changes, the index of a changes. When column changes, the index of b changes. So a3b1, a3b2, a3b3. So you can do one type of product where you can get a matrix out of couple of vectors. Okay, and in that case the size of the vectors actually doesn't matter. Okay, you see, if you have these two vectors, one column vector and another row vector. Okay, one has a size of 3 cross 1, the other having a size of 1 cross 2. It is going to give you a matrix of size. So when you do the multiplication, you'll get a matrix of size like this, uh, 3 cross 2. Okay, all functions of xi. Okay, and there will be total 6 terms, and you can do the integration with respect to xi. Okay, j d xi, and you can take q0 q1 out of the integration. So you can do this multiplication. Okay, after you have done the integration. Okay, why am I saying this? Let's say if I give you the values of q0 and q1. Let's say q0 is 100 newton per meter, and q1 is 200 newton per meter. Okay, so if I give you these values actually, okay, and if you internally do this multiplication and then integrate, okay, so the issue being there is you will have to integrate. You can have arbitrary set of numbers. I mean, it doesn't necessarily have to be 200. It can be, let's say, 235, and this thing also can be, uh, let's say, 119.5. Okay, so the integration could be difficult. Okay, you can keep them out of the integration, and you can simply integrate terms which are either 1, okay, or half, or something like that. Okay, so that would be quite easier for you to do the integration. Okay, and for that matter, this j term also is a constant. The way we have chosen x2 to be x1 plus x3 by 2, so that essentially gives you j to be x3 minus x1 by 2, or basically le by 2. So that can also come out of the integration. So anything with uh, I mean, because this element length could be something else also, right? 12.3 millimeter. Okay, something like that. It can be. So anything which can have an arbitrary real value, you can keep them out of the integration and perform the integration with terms of xi. Okay, so that way your integration becomes really easy. Okay, and also, why do I need this type of practice? Let's say you are trying to write a program in computer. So the values that might change is the element length, the value of the, the distributed load at the two ends. Okay, two ends of the element. Okay, that might change, and but this integration, this part will never change. Okay, so what you can do is you can do this integration, and you can save this whatever comes out of this integration. Okay, you can, let's say, you can put this j out of this integration, and whatever comes out of this integration, you can store that. Okay, so that part you can I mean, what you can make a routine whenever you are provided with the values of the element length and the traction values, these two. Okay, you can do this, so there will be a single multiplication to this matrix. So what you can do is you can keep this matrix evaluated through integration. এই পার্টটা বোঝা গেল কি বলছি?
sir.
That will help you in programming when you code a finite element program. Okay. That being said, today we are looking forward to uh, assembling matrices and vectors. Okay. Basically, so far, whatever example we have done, deliberately we have chosen to do a single element. Now we would like to do multiple elements. Okay. And I'll be taking the example of two linear bar elements, okay, to explain the process to you. So let's go back to the class of last Wednesday, when we had considered this bar. Physically, this was a slender component. Okay, what is a bar? Is just a deformable body, a continuum, okay, which is slender in nature. But we made couple of assumptions. Homogeneity, not that we cannot solve the problem without this, but for the sake of simplicity, homogeneity, uniformity, and and the length being quite larger uh, than the dimension of the, you know, the cross section. And so there was, so we'll consider the general case where there is an end load, and then there is this arbitrary uh, function, which is this distributed load on this rod everywhere. Okay, does the distributed load should the distributed load be everywhere within the bar? You see, I'm assuming that q is an arbitrary function, so it means, let's say, uh, if this is 0 and this is L, q can be a function like this as well. Okay, it only starts at a given x location. Let's say x star, that's where it starts. Okay, so so that is also allowed, an arbitrary function. And it if indeed q is like this, that means q is not continuous. Okay, or q is only applied to the part of the bar, then what is suggested is you take multiple elements. Okay, typically separating the part where there is q and and the part where there is q is 0. Okay, so basically what you can do is you can take two elements along the length. Okay, and that being said, it's not mandatory for you to have a discontinuous queue in order to have more than one element. You can choose to have more than one element whenever required. Okay, the major reason for which you take more than one element or multiple element or even more element is only to improve accuracy. Okay, that is a major idea. So the major reason. So I'm dividing this bar into two elements, element number 1 and element number 2, and then I'm since I'm taking linear bar element, each element has two nodes. Okay, so there are in total there are three nodes. We didn't cover this part, right? With more than one element, did you cover this part? এই পার্টটা কি আমরা কভার করেছিলাম?
No, sir.
No, sir.
Okay, acha. So what I'm doing here is dividing the geometry into two elements. Okay, two linear elements, uh, and but you see the variational statement or the v statement that I have. Okay, that actually is this thing. This variational statement is there for the entire bar. Okay, but what we will be doing here is, let's say for the left hand side. Okay, so the thing is, okay, a few more things I need to mention, that it is not necessary for you to divide the geometry into equal halves. Okay, or if you are taking 10 elements, you are not, it is not mandatory for you to take 10 equal segments within the geometry. Sometimes you want to have uh, unequal or non-uniform mesh. Okay, and let's say I would argue that for any non-zero distributed load, the stress is going to be a little higher, rather a lot higher compared to the at the fixed end compared to the free end. Okay, for example, if this rod is hanging due to its own weight, okay, then then at this end the stress is zero. Okay, if there is no other concentrated force, the stress at this end is zero, but maximum over here, and that stress changes linearly. Okay, so to argue that, let's say ea u double prime equals minus q, right? And if this q is a constant, if this q, you see the this q is going to be rho ag for this bar, and since this is a constant, so eventually we will have u to be a quadratic function, which means strain, which is u prime, is going to be a linear function, and eventually stress, which is simply Young's modulus times your strain, that is also going to be a linear function. So actually the fact that the stress at this end would be zero, that is one of the boundary conditions. You see, there are two boundary conditions. The first one being u0 is 0, and the second one being e a u prime, okay, equals 0, of which e times u prime, you see there is no concentrated force over here, it's a free end. Okay, of which e times u prime represents the stress, u prime being the strain. So this region is traction free, or for that matter stress free. Okay, so I would argue that since the fixed end is of higher chance of having stress, okay, and as we know, whether we choose a linear bar element or a quadratic bar element for an arbitrary function q, okay, it's a sine of x or whatever, uh, this we are only getting approximate solutions, and the way to improve approximate solution is by taking more and more elements. And since the stress is typically higher at the fixed end, so because all the reactions are coming from the fixed end, so I would argue that you take more elements towards the fixed end and lesser element at the free end. The technical term should be, they take fine mesh over here and take coarse mesh over here, okay, towards the free end. Now let us talk about the integration in the left hand side. Okay, the problem is, when now I look at this particular element, okay, uh, I would be treating it the same way I treated uh, the bar element that was covering the entire bar. Okay, and I mean the same set of shape functions same way I would define the variation. So for example, if I take element number 1, so there are two nodes 1 and 2. So xi for me, okay, is still going to be varying from -1 to 1, although now I'm only interested in one part of the bar. Okay, and let's, for the sake of simplicity, assume that this element length is L by 2 and this element length is L by 2. But then also xi would be changing from -1 to 1. That is how you take the natural coordinate. Okay, it simply scales down or scales up, but it is always going to be -1 and 1 at the two ends. Now x earlier was 0 and L. Okay, but this time x1 is actually 0, but x2, again for the sake of simplicity, if I take two equal elements L by 2, u, as since I do not know, it is going to be u1 and u2, and v similarly is going to be v1 and v2. Okay, so from this point onwards, the treatment is the same that we did for the previous case, where we took a single bar element along the length of the bar. So there would be two shape functions. So this one is -1 and 1 along xi axis, and this much is 1. So this is going to be n1, and this other line is going to be n2. Okay, and you know the remaining drill. So you have done linear bar element and quadratic bar element. I would expect you know. Okay, it should be by heart by now, that what to do next and how to get the element stiffness matrix. Okay, but that way we would be getting only the element stiffness matrix. But let's see what happens now. Now the thing is, if I take this integration, okay, I can split that into two parts. This symbol represents that the integration is being performed on the element number 1, where I can write it to be and this one means the integration is being performed on the second element. You see, if I cover the two elements, essentially I am covering the entire bar. Okay, this whole integration can be represented like this. Now if you recall from our earlier case, when I'm integrating EA u prime over a given element, no, it should not be 0 to LE. Let's say from x1 to x2. Yeah, I should be also writing it to be dx. Yeah. Because for xi, I know the limits. So if I'm doing this, we knew to write it like this: V transpose, V hat transpose, then the element stiffness matrix, then U hat. Okay. So for the first term, this V hat transpose would look like this: V1, V2, then the element stiffness matrix. Now, what would be the expression for element stiffness matrix? It would be EA by LE. Now, the element length I have taken to be L by 2. So, there goes L by 2. Then 1, minus 1, 1. And this is just the first term being integrated. Then U1, U2. Okay. For the second term, it is going to be V2 and V3. You see, If you look globally, not element wise, okay, so this thing is your element stiffness matrix. And now we would be proceeding towards something called a global stiffness matrix. But before going into that, globally, if you look at it, there are three nodes. Each node has one degree of freedom each. I mean, I can also draw it for you. So there is u1, u2. So here I have taken only the first element, since I have written u1 and u2. If I had done the second element, I'd be doing the same treatment. Okay. Now things that would change would be x1 would be L by 2, and your it is actually not going to be x1. It is going to be your x2, and this is going to be x3, which is L. U is going to be u2 and u3, and v is going to be v2 and v3. Okay. So similarly for element number 2, this is the expression that I'm going to get. Again, I had the freedom to choose elements of different length, and in that case, these two are not going to be L by 2 and L by 2. It would be the ones that I choose. Okay. Okay. So this is going to be the expression. Okay. Now, essentially, you see, I'm integrating a scalar equation. And if you think about it, the size of this vector is 1 cross 2. This matrix is 2 cross 2. And this is 1 cross 2. Sorry, 2 cross 1. Okay. So if I do the total product, in the end, I'm getting a matrix of 1 by 1, which is basically a scale. So can you do this product for me? Can you do this product and give me terms such as v1 times something within the parenthesis, v2 times something within the parenthesis, and v3 times something within the parenthesis? Can you do this product? এটা তোমরা এখন করে আমাকে বলতে পারবে ভ্যালুগুলো কত হবে?
হ্যাঁ স্যার, করছি।
Just one modification I need you to do, just to keep the things generic. Okay. K11, K12, K21, K22, K11, K12, K21, K22, okay, with superscripts representing the element number. Sorry. Okay, just do it like this, and let it be symbolic. In the end, when you are actually solving the problem, so you can substitute K11 1, K22 1, K11 2, K222 equals EA by LE, EA by, sorry, L by 2, and K121, K211, K212 equals K122 equals minus EA by L by 2. Okay, that you can substitute later. But for the timing, can you do this exercise involving the symbolic representation? এক্সপ্রেশন গুলো পাওয়া যাচ্ছে?
হ্যাঁ স্যার এলো।
আচ্ছা, ঠিক আছে। যাদের এসেছে তারা আর একটু ওয়েট করো। Okay. So you'll have some expression involving v1, v2, v3. And the coefficients of v1, v2, v3 will be having terms involving u1, e2, u3, right? So if I want to make, I mean, it might seem for the time being, okay, why am I complicating stuff? You see, I can only do handful of examples in using pen and paper, okay, only for the simple problems, okay. For example, bar, which doesn't actually require this complex steps, okay? But unless we learn how to do those complex steps, we would not be able to use these steps for more complicated problems, which cannot be solved unless you are that much organized. The only thing, the thing that matters the most, not the only thing, matters the most in finite element method, it is it being a subject which is best implemented through computer programming, is how you organize your problem or how you organize your solution steps. So this left hand side of ours, okay, will give us certain coefficients of v1, v2, v3, which will be having terms of u1, u2, and u3, okay. But can I write it like this: v1, v2, v3, okay, and then they would be multiplying, let's say, some linear function. I should be representing functions with different notation, some linear functions of u1, u2, u3, okay. And since they are linear functions, I should be in a position to write them like this: this whole matrix and times u1, u2, and u3. So there you have a matrix of size 1 by 3, or vector of size 1 by 3, and this one u1, u2, u3 is 3 cross 1, and in the middle the matrix size should be 3 by 3. So I need you to figure out this 3 by 3 matrix. Can you do that? So if you have already got the coefficients of u1, v1, v2, and v3, which are some g1, g2, and g3, so I can write in this format, which essentially is a dot product, okay, and then write this vector as this part. So this second vector basically contributes to this matrix and u1, u2, and u3. I need you to give me this matrix, and this matrix you would call the global stiffness matrix.
স্যার স্যার
বলো।
বলছিলাম কি এই যে ম্যাট্রিক্সটা ভি1 আর ভি2 আর কে ওয়ান ওয়ান প্রাইম কে ওয়ান টু প্রাইম আর ইউ1 ইউ2 এটা গুণ করলে ভি আর ইউ এর গুণে আর কে এর গুণে রেজাল্ট আসছে, শুধু ভি আর ভি এর আলাদা করে ভি এর সঙ্গে আলাদা আসছে না। ভি ইউ আর কে কে ওয়ান ওয়ান প্রাইম ভি ওয়ান ইউ ওয়ান কে ওয়ান টু প্রাইম ভি টু ইউ ওয়ান এরকম আসবে।
প্রথমত হচ্ছে there is no prime. Okay, so this is k111. That 1 stands for it is coming from element number 1. Similarly, k112 represents the stiffness term that comes from element number 2. Number 1. Number 2 is there would not be separate terms of v1 v2 and v3. I mean, yes, of course there would be terms separate for v1 v2 and v3. The thing is the coefficients of v1, coefficients of v2 and coefficients of v3 would be terms composed of this kij terms and this u1 u2 u3 terms. Okay, so this g1 g2 and g3 are going to be some combination of this k111 or k121 then u1 or something.
ওকে
স্যার একটা ম্যাট্রিক্স এসছে, বলবো?
ম্যাট্রিক্স এসছে তো? আচ্ছা ঠিক আছে, আমি দেখি আর কজনের আসুক।
এসছে স্যার।
ওকে,
স্যার এসছে।
এসেছে তো? আচ্ছা ঠিক আছে। So in the end, I can write the LHS of this expression. This is our V statement. And there is one thing without which V statement is not complete, which is this true for arbitrary V. Okay. When looking into the function space from which U belongs, which is a subset of all possible functions. Okay, the left hand side boils down to V hat transpose. So V hat transpose is what? Now I'll call it V hat transpose global. Okay, and what is that? V1, V2, V3. If I had to work with elemental V hat transpose, that would only have either V1, V2 or V2, V3. Now I'm taking the global V hat transpose, so therefore it has all the three. Similarly, U hat global is this quantity U1, U2 and U3. Since I'm working with linear bar element, so per element there are two nodes and each node has 1 degree of freedom. So if I were to represent that for any given element, element number 1 or 2, that would be either U1, U2 or U2, U3. But since I'm doing it for the for globally for the entire element, so it is going to be U1, U2, U3. And in the middle lies your element stiffness matrix, the global stiffness matrix, the so-called global stiffness matrix. Okay, so is this term 0? It is 3 by 3.
Yes, sir.
Okay, okay, acha. So is this term K111?
Yes, sir.
Is this term K121?
Yes, sir.
Yes, sir.
So only term that is a little surprising is K122 plus K211, right?
Yes, sir.
Yes, sir.
Is this how it looks for everyone?
Yes, sir.
সবার কি এরকমই আসছে না আলাদা কিছু আসছে? Anyways, this is the correct expression actually, and then you can substitute for the expressions for K11 and K12 from either of the elements. But all I'm trying to say here is essentially this is a stiffness matrix from the first element, and this is the stiffness matrix from the second element. Okay, and this is how you assemble within the global stiffness matrix. Okay, what happens is the stiffness of a given uy adds up from different elements. Now for 1D problems, okay, the two elements share only one node. What I mean by that is that there is only one term, one diagonal term, which is seeing any change. That's where the adding occurs. Okay, so what you do is you start with a blank stiffness matrix, and you already know the size. The size is same as the length of V and length of U. Okay, so you start with a blank matrix, and you already know how to program this, right? If you start with a blank matrix, then for each term you keep on adding terms from different elements. Now in this case we see a merge of two terms only for a given diagonal element. It's because there is only 1 degree of freedom per node. Okay, and uh, the two elements are only connected through a single node. For example, if there were more than 1 degree of freedom per node, okay, so not only there would be addition in the diagonal terms, but also there would be addition in the off diagonal terms. Okay, so when you would be doing Euler-Bernoulli beam element or any form of beam element, okay, there this there would be off diagonal terms as well, where you see this sort of addition. Okay, also imagine in 2D two triangular elements. Okay, this one has 3 nodes, no mid-side node, so only corner nodes. If two triangular elements are connected by obviously they would be connected by a total side, which means there would be 2 nodes. And also in 2D there are 2 degrees of freedom, so you can move in x and y per node. So each node has ux and uy. Okay, so there you would see that the addition happens not only on the diagonal terms but also on the off diagonal terms. Okay, so since in this case only 1 degree of freedom is being shared, not just one node but only 1 degree of freedom is being shared with two elements, that's why the addition happens only at the diagonal term, at a single diagonal term. Okay, and as you can imagine, if I keep on taking more than one element, more than two elements, okay, let's see, if I divide the bar into 4 elements, I simply need to be adding the stiffness matrices like this. Okay, but if I were to share more than one degree of freedom or more than one node, okay, simply adding the stiffness matrices would not work. Okay, I mean simply representing the stiffness matrices with this overlap would not work. Okay, so what I'll have to do there is uh, I'll have to globally number all the degrees of freedom. For example, in these two triangular elements, I can number the degrees of freedom like this. And we will do CS triangular elements in later class, but I just want to explain this right now. U1, U2, then this for this one, U3, U4, U5, U6, then U7 and U8. And similarly, the V matrix would also be V1 to V8. Okay. And then I need to note down the element stiffness matrix for one of the elements. Okay. And then instead of numbering them as 1, 2, and 3, I would number them with global numbers. For example, for the second element, the numbering should be 2, numbering should be with degree of freedom 3, 4, 5, 6, 7, 8. That's how you number the rows. And 3, 4, sorry, that's how you number the columns, and that's how you number the rows. When you do that for the second element and also for the first element using the global numbering, then uh, when you form the global stiffness matrix, okay, and that would be of the size 8 cross 8, and for every term in the global stiffness matrix, every ij term is a summation of the ij terms, okay, for each element. Okay, chances are some of the terms will not be present in a given element. For example, the 7-8 term or 7-7 term or 8-8 term or 8-7 term would not be there in the first element. Okay, so we assume that term to be 0. That means this element doesn't contribute to stiffness on this node. Okay, so if certain certain indices are not present in a given element, we'd assume that or the element stiffness matrix of a given element, then we'd assume the corresponding term is 0. Okay, and we would be adding the terms to that to the global value. If sorry, the we would be adding all the terms from the element for a given index to get the value of the global term. Now, this is with the left hand side. What should we do for the right hand side? You see, the right hand side is integration 0 to L qv dx plus p times vl. Okay, again, q is an arbitrary function. I can write it to be integration over the first element, integration over the second element, and then p times vl. But I have taken two linear elements with 3 nodes. So there are u1, u2, and u3 at the 3 nodes. Okay. Similarly, there are v1, v2, and v3. So essentially, I'm talking about v3 over here. Okay. And let's say if I integrate this one, I'm going to have v hat transpose for a given element, elemental, and then the elemental force vector due to the distributed load. Okay. So essentially, for the first element, it is going to be v1, v2, fq1, and fq2. Similarly, for the second element, it is going to be v2, v3 times fq1, fq2. Okay. Now, can you do this multiplication? Essentially, these are all again dot products. So essentially, you will end up having the dot product. Okay. So can you do this multiplication? You'll end up having the scalar value. So can you do this multiplication and represent it like this, like the previous case, or for that matter, v1, v2, v3 times something. Actually, this is very simple. It is going to be, as you can see, fq1 sorry, I also need to mention the element number, right? So if q11 1 2 the number should be here. If q1 1, if q1 2, that's coming from the first element. If q2 1, if q2 2, coming from the second element. So this is how it is going to look like. And again, for the force vector, what we did was simply adding the coefficients of the like terms. So v2 was present in the first element and v2 was present in the second element. So what we did was we took the term for v2 and added them up. And again, if we were to work with 2D elements, or if we were to work with beam elements where we would encounter more than 1 degree of freedom, that addition would happen not just at a given value. Okay, there would be a multiple location where that addition happens. Okay, so in the end, if this is our v hat global transpose, so we have this expression. So this is our global force vector. Okay, so in the end, we'll have this transpose, then combining the left hand side and the right hand side, we would have this expression. The global stiffness matrix, the global U hat minus if global equals 0. Again, it's a dot product. Okay, and if you think in terms of the coefficients of v1, v2, and v3, so actually you'll be having 3 equations. Okay, where for example eq1 is kg11 u1 plus kg12 u2 plus kg13 u3 minus fg1. Okay, and so on. and this equals to 0. Okay, this whole dot product can be represented like this. Okay, and you know that the variation is arbitrary, but except for v1, because you see u1 u1 is 0, which means these are not three independent set of equations. Only two of them are independent. Okay, and v, which since u1 is given, so v1 is essentially 0. It's not because u1 is 0, it's because the value of u1 is known. And since v1 is 0, you cannot play the arbitrary game with u v1. So this term is not there, it's 0. And you cannot determine from this expression what is the value of equation 1. Okay, so you do not know the value of equation 1. It can be 0, it can also be non-zero. But look at these two terms. For any arbitrary set of v2 and v3, this expression is 0, which means in my mind I can set v2 to be 0, then also this expression is 0, and I can take v3 to be 10, then also this equation is 0, which means equation 3 is 0. And I can also in my mind imagine that v3 is 0 but v2 is 10, which implies that equation 2 is 0. For this to be true for arbitrary v2 and v3, equation 2 is 0 and equation 3 is also 0. But I do not know about equation 1, and since I do not know, I'll call it R, the residual. And eventually it will turn out to be the reaction force. So all I'm saying here is, in the end, we would write it like okay. Now, the second and the third equation are true, but the first equation may or may not be 0. So I need to add this residual over here. And I am not solving for u1, u2, and u3 from the set of three equations. There are indeed three equations now, three independent equations, but I am not solving for u1, u2, and u3. I am solving for u2 and u3 and r1 over here. Okay, so these are the unknowns. Okay, এই অবধি বোঝা গেল?
Yes, sir.
কারোর বুঝতে অসুবিধা? আচ্ছা, যদি অসুবিধা না হয়, then try to so these are your assignments. Take Q equals okay. Where Actually, I'm going to give you only one assignment today. And divide the bar into two quadratic elements of lengths L by 3 and 2L by 3. Okay, where L is 1 meter. Okay, and solve for nodal DOFs, basically U values, and stresses. Okay, and plot maybe in Excel, and if you are comfortable in MATLAB, U and sigma as functions of x. X goes from 0 to L. So basically, what I'm trying to say here, imagine you have this rod, and if you're revolving it with an angular velocity of omega, okay, then essentially in the rotating frame, this x is rotating actually. In the rotating frame, this is how the problem is described, taking q equals this much. Okay. Achha, by the way, Young's modulus is 200 GPa. So what you need to do, you need to divide this rod, and you need to be staying in the rotating frame. You are doing the entire analysis in rotating frame. You need to divide it into two elements of length L by 3 and 2L by 3. You're supposed to take quadratic elements. That means 3 nodes per element and quadratic shape functions. Okay. And the value of L is given. Every term in the Q value for them has been given except for X because it's changing. You're supposed to find out, you see there would be 3 nodes per element. So you're supposed to find out the nodal values of U and the nodal values of the stresses. Okay. And plot these values as functions of X. Okay. So this is your job. এটা করতে পারা যাবে মনে হচ্ছে?
ট্রাই করে দেখছি।
হ্যাঁ, তো এটা ট্রাই করো, ঠিক আছে? এতদিন যা যা শেখা হয়েছে, how to assemble a global stiffness matrix, how to do a quadratic bar element, put everything into it, okay? And then try to plot it. So what you can think of this as, this is a proper assignment, okay? So make a fair copy, and whether you plot it in Excel or whether you plot it in MATLAB, take a printout, okay? And you are also free to do that in a graph sheet as well. If you don't want to take a printout, you can also do that, okay? But you need to determine the stresses and the degrees of freedom as functions of X, and then you should plot them, okay? And you attach them, so it's just make it like a lab report or something, okay? বোঝা গেল অ্যাসাইনমেন্টটা?
Yes.
ওকে, কোনো ডাউট রিগার্ডিং দ্য অ্যাসাইনমেন্ট, বা মনে হচ্ছে যে এই জিনিসটা করা যাবে না এই কারণে? ওকে, তাহলে আমি ধরে নিচ্ছি এটা করা যাবে। হ্যাঁ বলো।
স্যার, যখনই কোনো কোয়াড্রেটিক এলিমেন্ট নেবো সবসময় কি মাঝখানের নোটটা দুটোর মিড পয়েন্টে হবে নাকি আমরা যে কোনো আরবিট্রারি পয়েন্টও নিতে পারি?
দেখো, you were free to choose anywhere ideally, But if you are willing to use that particular expression with 7 and 8 and 16 and 1 and all those things, okay, 7 and minus 8 and 16, if you are willing to use that expression, that only arrives there by taking x2 to be x1 plus x3 by 2. আর আমার মনে হয় না এক্ষেত্রে তোমার কোনো কারণ আছে যে you take x2 anywhere other than in the middle, okay, because that's the standard practice. And actually that second node is referred to in technical terms, it is referred to as the mid side node for a reason, because it lies in the middle of the side. So whether you use ANSYS or Abacus or whatever finite element software, they call it a mid side node. Now that being said, you might be thinking, and that's what I'm anticipating, that you might be thinking that there is certain amount of mesh refinement required for you to study, since the q itself is a quadratic function of x, you want to do a mesh refinement, but that you are actually doing already. You see, you are dividing the geometry into two elements, of which the first one is smaller, okay, half the length of the second one. So if mesh refinement is your concern, that has been already done. Yes, of course, if you had taken the first element, even in the first element you had taken the second node, the middle node, okay, towards the origin, okay, so this is the origin. If you are to take it closer to the origin, okay, you would get even better result, okay, but I would suggest don't go up to that length. That's not required.
Yes. Okay.
Okay, I'm sure it's going to be challenging, but if you have any difficulty, just let me know. Okay.
ওকে স্যার। স্যার আরেকটা জিনিস, লিনিয়ার বার এলিমেন্টের যে প্রবলেমটা ছিল অ্যাসাইনমেন্টে, যে থার্ড লোডিংটা Q1 ইকুয়ালস টু 0 এন্ড Q2 ইকুয়ালস টু 100 নিউটন পার মিটার, এই লোডিংটা মানে ভিজুয়ালাইজেশনটা বুঝতে পারছি না, মানে কিরকম লোডিংটা,
কিরকম?
ফার্স্ট নোডটাতে 0 আবার সেকেন্ড নোডটাতে 100।
না, মানে it is linearly changing 0 to 100. আমি হয়তো টার্মটা Q0 Q1 লিখেছি, but it's at the two boundary nodes, okay, so whether the element is linear or quadratic, I do not know that, okay. This is how the Q is changing. Let's say it is a quadratic bar element, then this is how the Q is changing.
Oh, linearly varying load.
Linearly varying load.
Okay.
You see, if I were to give you the values of Q at the three different nodes, let's say this is the value of, this is the Q1, this is the Q2, and this is the Q3, let's say. And let's take the example of a quadratic bar element, and if Q is varying using the same set of shape functions as U, which is not mandatory, then you can write this integration, the element force vector. So you can write it to be n transpose n q hat dx. বুঝতে পারলে কি করলাম আমি? Because q is also n times q hat, where q hat is q1 q2 q3. যদি এরকম দেয়া থাকতো যে তিনটে নোডে q এর ভ্যালু দেয়া আছে, and you are also been given that q is changing with the same set of shape functions like a quadratic function, okay, then this n hat is coming from that expression v equals n transpose v equals v transpose n transpose. It is coming from there, okay. So v transpose I have already taken out, so in the force vector v transpose doesn't appear, ঠিক আছে? তো সেক্ষেত্রে এরকম ভাবে করা যায়।
লিনিয়ার সেক্ষেত্রে লিনিয়ার বার এলিমেন্ট নিলে দুটো নিতে হবে, অথবা একটা কোয়াড্রেটিক নিয়ে করতে হবে, সিঙ্গেল লিনিয়ার বার এলিমেন্ট দিয়ে তো হবে না মনে হয়।
না, সিঙ্গেল লিনিয়ার বার এলিমেন্টেও হতে পারে, তো কোনো অসুবিধা নেই। তো ধরো সিঙ্গেল লিনিয়ার বার এলিমেন্টও আমি যদি বলে দিই যে q is changing like a quadratic function, you see in this product, okay, in this product the size of the vector doesn't matter. Let's say if it is a linear bar element, so this one is going to be 2 cross 1, and this is going to be 1 cross 3 if I take quadratic. So the product would be 2 cross 3. No issue. It's actually a dyadic product.
Yes.
মানে কোয়াড্রেটিক বার এলিমেন্টে কিউ লিনিয়ারলি ভ্যারি করতে পারে, লিনিয়ার বার এলিমেন্টে কিউ কোয়াড্রেটিক ভ্যারি করতে পারে। বোঝা গেল?
হ্যাঁ স্যার।
পার্টিকুলারলি আমি এটাকে n ট্রান্সপোজ n কখন লিখতে পারি? যখন u and q are changing with the same set of shape function. It means the bar element is quadratic and also the shift q is changing quadratically. বোঝা গেল?
হ্যাঁ স্যার, বুঝলাম।
Okay. Okay. So actually that would be helpful for you, because in this case if you take that thing x2 equals x1 plus x3 by 2, okay, that's I suggest you take that. So x is a linear function of xi, which would mean that if q is a quadratic function of x, then q is also a quadratic function of xi. So you can use this sort of a treatment over here. That would be really helpful for you. Okay, so we'll stop the recording now, and we'll meet on Saturday at 11.
Okay, sir.